Thank you for coming, everyone. Before, if you can focus, thank you for stopping all the side conversations. Thank you for stopping all the side conversations and welcome to the seminar. Please silence your phones and stop side conversations. Also at the very end, when we have questions and answers, because this is being recorded, please wait for the microphone to reach you. And then ask your question so it's recorded. Just as a reminder before introducing the speaker that our next highlight seminar of the Andlinger series will be Esther Takushi from the University of Stony Brook on October 19. And tomorrow we have a special guest, the Minister of the Environment of Chile, Marcelo Mena, who's going to be talking about Chile's energy and environment. So these are kind of what's coming up. So now I would like to extend my warm welcome to a good colleague of mine, Cristina Archer. Cristina is actually Italian. She did her undergraduate degrees and bachelor's and master's in civil and environmental engineering at Politecnico di Milano, and then she went to the Bay Area where she did a master's in meteorology at San Jose State University, and then she joined the group of Mark Jacobson at Stanford where she did her PhD in civil and environmental engineering. She then stayed on with Mark for a couple of years as a postdoc, for 1 year as a postdoc, and then did a couple of stints in industry. She worked as a modeler in air quality for the district of San Francisco from 2005 to 2007. And then she worked for a year as a research associate at the Carnegie Institution for Science. And then she went back to her academic career at the California State University as Chico as a assistant professor before joining the University of Delaware in 2011, where she's now an associate professor in the College of Earth, Ocean, and the Environment at Delaware. And she has a joint appointment between Physical Ocean Science and Engineering program and the Department of Geography. Today, she's going to mostly talk about her wind energy work, but Cristina's work goes beyond just wind. She works on air quality modeling and a lot of the problems and the applications of boundary layer meteorology. So, Cristina, thank you again for accepting our invitation, and the floor is yours.
My pleasure. Thank you so much, Ellie, and thank you everybody for being here. This kind of talk is actually a pleasure to give because, first of all, wind turbine wakes are my new favorite topic. So when I find a favorite, I want to share with other people what I love. And second of all, it happens to be a good time to talk about hurricanes. So I will show you some super cool stuff about Harvey that is very, very preliminary today. But again, wind energy, turbulence, and hurricanes, you might think they have nothing in common, but I will approach these three topics from the wind turbine wakes point of view. And hopefully you will see that you can indeed save lives and money with my research. A quick outline of my talk. First, I would like you to understand why wind turbine wakes are so important from the local to the regional to the global scale. I've actually looked at this problem at all three scales. But then I'm going to focus more on the local scale, the one that is of interest to me today, and look at wind farm layout optimization, atmospheric stability effects on wakes, and if we have time, and if you still have energy to follow, maybe I'll talk about some compressibility effects. All right, first, what are wind turbine wakes? And I want to show you the only two pictures that I know of, the only two photos visible to the naked eye where you can actually see wakes. These are absolutely extraordinary. You will never see a wind turbine wake with your eyes if you stare at a farm, no matter how many days you go back and try to look at it. It's very unusual to be able to see it. But the conditions at these two offshore farms, which are, okay, maybe not. Okay, these are two offshore farms, Horns Rev 1 and Horns Rev 2, very original, offshore of Denmark. They are up here. Since they are offshore and the air is saturated with moisture, sometimes you get the right conditions and you get this condensation and you see the wakes. So there are these plumes that form downstream of the turbines where the air is turbulent, so it's choppy and dynamic. And more importantly, the wind speed is dramatically reduced. So you had a high wind hitting the turbine is put into motion by that momentum, and then downwind, you're left with less wind, with a wind speed deficit. So this wind speed deficit can be seen not with the naked eye, but with a tool called LiDAR, which is a electromagnetic wave. It's a laser-like device that can give you an idea of what the wind field looks like. And the wakes show pretty clearly as these areas with blue, light blue colors, which means low speeds, versus the high speed area with the reds that was hit in the turbines. So the wakes kind of like oriented themselves with the wind direction more or less, and they have lower speeds. You can see it in these horizontal cross sections. You can see it in this beautiful vertical cross section. Here's a turbine, and here you can see again the wind speed distribution, the lower speeds. And this is what the LiDARs look like. Actually, this picture down here is not as pretty as the other two, but we took it with my field campaign that we did in Lewis, Delaware, where we have a single turbine, this little point here. Can you guys see my mouse? See? This is where our single turbine, a 2 megawatt Gamesa, is in Lewis, and we power all of our marine operation labs with the turbine and actually generate enough electricity to make a profit, and that's how we pay a couple of graduate students per year, thanks to the turbine that we have. So you can see it if you're lucky. Once in your lifetime, you can see a wake with your eyes. If you have a LiDAR, you can see them more often. Or you can have fun and simulate them. So I'm showing you here two examples of what a wake looks like in simulations. These are both large eddy simulation results. One is a single turbine on the left, and on the right is an entire farm with 48 turbines. And again, the colors are red is kind of like high wind, and blue is more like reduced speeds by a lot. So red is like 10 meters per second, and blue is more like 3 meters per second. So you lose 70%, you can lose 70% of the momentum in a wake. But it's a dynamic feature, and believe it or not, hard to simulate and predict. But why do we care about this? Well, it always boils down to money. So if you have a wind speed deficit, what that means is that the turbines behind the front row turbines will produce less because there's less wind hitting them. And this farm here is Lillegrund offshore of Sweden. It has 48 turbines. And this plot comes from another study. This is our data that we have. And it shows you what happens as you go deeper and deeper into the farm. So the front row basically produces 100%, it's the blue line here, produces 100% of what it can for the speed for all the directions. But for the directions of alignment, even just the second row dips down and produces maybe 30% of what the front row can produce. And then the next one, 30%. The next one, 40%. It doesn't recover. So for certain directions of alignment, in this case, southwesterly flow, so it's aligned with these rows, the inner turbines all produce 30% of what the front row turbines produce. So it's a very large loss. And it's not like we don't know about it. We know about it. But what can we do to improve this, to maybe mitigate this problem, or to be smart in the first place about it? But before we go there, I would like to skip briefly. Instead of going to regional, I'm going to go to the global scale really quickly and show you why this is interesting also from the global scale perspective. So we can look at wind speed, the distribution of winds worldwide at the hub height of wind turbines, which is about 100 meters above the ground. And this is what the wind speed distribution on an annual average looks like. So you can see that there are regions with high winds, the red colors, regions with blue winds, regions with less wind, the blue colors. And this is what is actually going on today. This is the actual wind distribution. But what I was wondering was, what if we had a lot of turbines everywhere? Would we be able to alter this distribution of winds? And if so, how? And how much power could potentially be extracted? In order to do this, we had to not only run a model, a global model, a global circulation model. This is actually a complex model that has such a long acronym that I actually have to read it myself. It's called Gator GCMOM, which stands for One-Way Nested Global to Regional Gas Aerosol Transport Radiation General Circulation Mesoscale and Ocean Model. Not my idea. So it's very good, but it didn't have wind farms in it. So we decided to add wind farms or parameterize wind farms in it. And the way we did it was treating them as a sink of momentum, basically sink of kinetic energy. So in a grid cell where there's a farm, there's a sink of kinetic energy that is proportional to the speed and also proportional to this power curve, which tells you how much power a turbine can generate as a function of speed. So we have speed here and power. This is a classic power curve of a turbine. This is one specific turbine, the repower, 5 megawatts, but that's what they all look like. So we put this in the model, and then we were able to calculate backwards how much speed is left after you take out all this kinetic energy. So here's what happens when you add turbines everywhere, and I mean everywhere. Every single grid cell of the model at 100 meters hub height has now turbines in it. So on the left, you can see the power extracted, so the terawatts, tera equal 10 to the 12th. Watts of power extracted. So the mean is 253 terawatts. By comparison, the global electricity demand today is 2.5. And on the right, though, is the distribution of wind that you would get after that. So all the red and the yellow and even the green is basically gone, and you're left with the blue shades. So you have a different world if you do this. I was like, okay, that doesn't make any sense. We're never going to do that. What happens if you do it only over land? So now we extract this energy only over land, and now the warmer colors show up again in the distribution. We still can extract something like 80 terawatts.
The density of your wind turbine?
Yeah, we varied them.
Every 10 feet?
No. 7 diameters times 4, and then 14 times 4, and then 8 times, we did a bunch of cases like that. But anyway, since you asked, here is basically the result of this. On the x-axis is basically how many turbines we put in, which is a function of how I space them. So the more turbines here, the tighter the spacing. This is for 7D times 4D, which is a little tight, but it's still not uncommon. But the point that I want to make is that because we are considering the effect of the turbines of that extraction in the global circulation in real time, the wakes are basically taken into account. And what happens is that at one point, there's a saturation. Basically, it doesn't matter how many turbines. You can put in hundreds of thousands more turbines. You're not going to get a single watt extra because you have reached this saturation. The black line is what you would get if you were just expecting a linear behavior. So it is linear for a while, but then it's not. And the same thing happens over land. So if you only put turbines over land, you get a saturation like this. And believe it or not, even in a farm, in a single farm, you get the same curve. So you have a certain area, you put some turbines in, and for a while you double, triple the turbines, you get double, triple the power, and then at one point you get this saturation. So it's a curve that manifests itself at all scales. But this exercise was just to try to assess what the theoretical wind power potential of Earth would be. And we now have it. It's about 250 terawatts, and it's indicative of this saturation that was reached. And the technical wind power potential is about 70 terawatts. And so we were able to do this because we took into account that extraction of momentum in the model itself. So the wakes were responsible basically for the difference between this black line and the blue line. So they're very important. Now I want to go to the regional scale and talk about what happens during hurricanes. And I have a short video clip for you that will save me some time in my talk.
Well, if there is just one word to sum up the destructive power of a hurricane, it might be Katrina. But what if a storm like Katrina could be weakened or even stopped? It may sound unlikely, but as Jonathan Betts tells us, there's a new study out that says it's possible if the government looks in the right place.
John Carbone has faced a long road home. After Sandy destroyed his New Jersey neighborhood 2 years ago.
It just washed homes away. You know, it came on board,
And he's very, very mean to everybody.
For too many along the coast, Mother Nature's fury could not be avoided. But a new surprising study may change that.
Surprise is not enough. That was a start.
All right, guys, let's start.
Environmental engineer Cristina Archer discovered something may indeed stop a hurricane. Of all things, the windmill.
We found out that the Humboldt turbines actually have way more power than we thought they did.
Using complex computer models, she, along with the team at Stanford University, realized wind turbines used to make electricity have an unexpected effect on hurricanes. Their spinning blades absorb their power.
They can actually weaken the hurricane, reduce the wind, and on top of that, reduce flooding in coastal communities. How cool is that?
The idea, she says, is build them up, and it is a lot. Think tens of thousands off the coast. But they might break apart even monster storms like Katrina.
This is without turbines, and this is with turbines.
Practically fill the Gulf of Mexico with 500,000 turbines, and Katrina's surge drops by 4 feet, she says.
So the hurricane, as it approaches the turbines, begins to fall apart.
Yeah.
Critics frankly laugh. They say what she's suggesting is probably impossible. It's too early to speculate about cost. And America doesn't yet have any offshore wind farms. The only one on the coast is in New Jersey, and it just has 5 turbines. Even some green energy supporters are doubtful.
I don't think there's an economic justification for it. So if you're putting 10,000 as opposed to 2,000 offshore to offset a hurricane that might come.
Skeptics doubt whether these turbines could even withstand a hurricane. Well, this wind farm in New Jersey was the first to put it to the test when Hurricane Sandy plowed through.
The generators were turned off before the storm, but the windmills survived.
They stood and then they were up and generating within a couple of days.
If we were going to say this is
Yeah, I mean, I'm not proposing that we actually do it. It's more about, wow, there is a benefit that we didn't know.
It intrigues people like Carbone, who lost everything.
It sounds wonderful if it works.
That's a big if. But it does bring hope that winds of change will one day stop a storm.
All right, I thought I'd share this. So it was actually an exciting day when the Al Jazeera crew came on campus and filmed everything. But let me show you actually some of those plots that were displayed during the video. The model is the same, and we use the same parameterization. And so you know we did Katrina, Sandy, and Isaac in this study. And we placed turbines wherever the bathymetry was favorable and not past 100 kilometers from the coastline. And we did a bunch of sensitivities to where we placed them, how many, and what spacing. But here are some results for Katrina. And on the left, you see the results without turbines. So this is a simulation of Katrina as it was, and this is wind speed. So you see the high winds around the eye. And the red dashed line represents the limit of the farms. So we placed farms all over the coast here, 450,000 turbines. And on the right is the same field, but with turbines at this time, 2 UTC on the 29th. And as you can see, by comparing the two, the speed in the location where the turbines are is in the purple range, whereas before it had blues and even greens and yellows. So it went from something like up to 30 to 35 meters per second down to less than 10. This is actually the wind speed difference, so it pretty much coincides with the position of the turbines. And this plot is not very cool right now, but it will get cool in the next slides. This is the pressure, sea level pressure difference. So the difference between the sea level pressure with turbines minus without turbines. So look at what happens as the storm evolves and the eye gets closer to land. Because there was all that reduced wind speed, there are some tongues of lower winds that make its way into the eye of the storm and actually kind of weaken it, if not even split it. And the sea level pressure actually rises dramatically because of this. So in a sense, we're filling the eye of the hurricane with higher pressure, so it weakens the hurricane. And then the effect continues even after the hurricane has passed. So we did a lot of, I don't want to focus too much of the conversation about this study, but it was very interesting. We also did simulations with offshore turbines only offshore of New Orleans, and we still got reductions, and the most interesting result was the storm surge reduction. Basically, Katrina would not have flooded New Orleans if we had had such a large wind farm to protect it. I'm investigating this further right now. We have a new hybrid wind farm parameterization. So it's a more advanced way of treating the farm, and it has very, very promising results because, for example, for TKE, the circles or the squares here represent LES results of what the distribution of turbulence should be downstream of a turbine, or actually downstream of a farm. And the red line is what the current parameterization in this common weather model called WRF. This is what it predicts today, so it's off. And our parameterization instead is very close to what the fine resolution results suggest. And so here's the little gift for you that I promised you earlier. We are doing this for Harvey, which is, you all know what it did to Houston a couple of weeks ago. And we have some evidence that if you place turbines in front of the coast of Texas, and we're talking here something on the order of 10 to 100,000, so you would reduce precipitation over land. So this is a plot of the difference in precipitation, cumulative precipitation in one day before. So again, the difference between with turbines and minus without turbines. So the blue is the reduced precipitation along the coast at the expense of enhanced precipitation ahead of the farm. So basically the presence of the farm enhances precipitation at the farm due to convergence and enhanced surface dissipation and surface friction. But then there's divergence after it, and that causes a suppression of precipitation. So this is very exciting, but again, it's very preliminary, and this is unpublished, and so don't quote this yet. Wait a couple of, maybe a year, and there will be a paper. Okay, now to the more fine scale stuff that I'm interested in. And the first one is wind farm layout optimization. Again, I know there are wakes. I know that they reduce the power, so how can we avoid this? I've looked at this problem from the large eddy simulation point of view, so computational fluid dynamics at fine scale. This slide is very full, and some of you are very interested in these details, so I'm going to leave it up and mention a couple of things. If you don't care about LES, this might be a good time to maybe check that silent phone of yours for any urgent messages. So you have a couple of minutes of break while I briefly mention to those of us who are nerdy enough to like this stuff. This is the SOFA. It's a package that was developed at NREL, the National Renewable Energy Lab. It's a finite volume C++ based code, and in this case we used 80 million grid cells to resolve the Lillegrund wind farm. It has 48 turbines, and they are the 2.3 megawatt, the Siemens 2.3 megawatt turbines. This is the most tightly packed wind farm in the world. It has a spacing of something like about 3 by 4, but it's actually 3.3 and 4.3 diameter, so they're very close to each other. So it's a very good farm to study wakes because there are a lot of wakes. We did a resolution of down to 3.5 meters around the blades, and then 7 meters in a buffer zone and 14 meters outside. And the highlight line here is the scary one. Each run of this thing takes about a month and a half on a high-performance computer cluster with 144 processors running all the time. And what do I get after 45 days? I get 30 minutes of simulated time. So to get 30 minutes, I need to run this thing for 45 days. So it's a very, very computationally intensive kind of simulation. So if I want to try to do any kind of optimization with a tool like this, I'm going to have not 10 lives, but 100,000. Actually, I calculated, I forgot, the number was insane. Like I have to live 6 million years or something like that to wait for this. So it's not going to work for optimization. But what it does, if I do a suite or a set of these simulations for key changes, then I understand the processes, and then I can simplify them, do a zero-order version of them, and be fast. That's what we did. So here's an example of what we can play with once you have this tool. On the left is the original layout, the 48 turbines as they are today. And on the right is just a slight variation of them. Basically, every other row, I have shifted a little bit so that, let's say, if you look at turbine 15 and 14 here, they're perfectly aligned. But here, they're off. So basically, 14 now is not behind 15 anymore. You have to go all the way to 13 before anything is right behind 15. So it's called a staggered layout. And I've done this every other row. Not a big deal. At construction time, building this or building the original costs the same. But for southwesterly flow, which is the one I'm showing you here, there is actually a significant difference in generation. So the original layout produces about 695 kilowatts per turbine on average. And with the staggered, it's 787. So we got almost 10% or more improvement in power. And the losses go from 35% to 20%. So this is it's a lot. So you know the wind industry gets excited about changes in performance by 0.5%. Because 0.5% over a medium-sized farm is on the order of $1 million a year of gains. So 10%, people faint, basically. So it's so much better. But let me clarify, this is for 220, for a direction from the southwest. So it's one specific direction that happens to be good. So for example, if you do northwest now, so the wind instead of coming from the southwest comes from the northwest, then they're actually producing the same. If not, actually the staggered layout produces a little less. So now you're like, okay, so 45 days, 90 days, it's already 180 days to get these 4 plots. You can imagine that if I want to do all the directions of interest, and then now I want to move turbine 15 in position of that, and I want to stagger, it's not going to work, right? So what we did was coming up with a zero-order model, which we call geometric model, GM. And this model is called geometric because it's based on a few geometric properties that are relatively easy to calculate in farms, such as the fraction of the rotor area of a turbine that is blocked by any turbine upstream, assuming that there's like a cylinder coming out, as if the wake was a perfect cylinder that did not expand. So this is not supposed to be a model of a wake, it's just a property that I can calculate. So for example, if I have turbine T3 here, and T1 is upstream and the wind comes from this direction, if you look at a cross section of the two, you see that T3 is blocked in this area that is shaded in red. So this fraction is called the blockage ratio. And similarly for T2, turbine T2 is here, is blocked by a tiny, tiny bit by turbine T1. So I can calculate these fractions and I call them the blockage ratio. And I also can calculate something called the blockage distance, which is some kind of a weighted average of how far do I have to go upstream before I am blocked by anything. So these are geometric properties. And so I now can calibrate some fitting coefficients for these geometric properties. I calibrate them so that they match my LES results. And the results are very good. So these are basically some selected rows for a direction of southwesterly. So for example, row C is this one. And you can see that the observations in blue and the geometric model in red and the LES, they are matching very well, except the geometric model takes me 0.1 seconds, and the LES takes me 45 days. Okay, so I can forgive a little bit of inaccuracy for 0.1 seconds versus 45 days. So we basically developed this into a software, and we were able to do some very cool stuff in terms of optimization. So these are 2 random examples. This is a farm in Finland, which was one of the most complicated and most constrained farms I've ever heard of. Every little circle you see here, every shaded area is a no zone. You cannot build there. And it's very complex, and yet we were able to create a very nice layout, uneven, irregular. Every little dot is a turbine. This one is Krieger's flak, which you may have heard from a couple of months ago. This is the cheapest. So this farm is going to be built with no subsidies of any kind, and it bid to generate electricity from offshore wind at the cheapest price ever on Earth today. So it's a very successful design, and we designed this layout, which actually is very similar to the design that they are actually the winning design. So we're very proud of that. We were very similar idea. Another important parameter that can impact the wind farm production for the same wind speed. Imagine this, you have the same wind speed at the same hub height for the same layout, so the same farm. But you can have an atmospheric stability situation now that will cause your power to be different. In some cases higher, in some cases lower. Atmospheric stability is actually a very difficult, complex concept, and I consider myself an expert in it, and the more I study it, the less I understand it. So now you're getting me at the moment when I actually have a hard time defining what stability is. So I'm going to give you some kind of an intuitive definition, and it's probably not very accurate. But when the atmosphere is unstable, think of it as a pasta bowl boiling on your stove. And I'm Italian, so I love pasta examples. So hopefully you remember what happens. So when you're boiling your pasta, you're boiling it from below. So you put the flame underneath. Why? Because if you heated your pasta bowl from the top, heat doesn't like to go down. It's not gonna make it effectively or efficiently boil. But if you boil it from below, you're making the density lower, and when something is buoyant, it goes up and it mixes your pot. So think of a boiling bowl of pasta with all those eddies and that turbulence. It pops up, it bursts, so it's very dynamic. That's an unstable atmosphere. In the afternoon, in the summer, the sun has cooked the surface for a while. Surface is very hot. It cooks the atmosphere from below. It makes these eddies, this circulation very vigorous. On the other hand, you have a stable situation at night when the land is very cold and everything's still and stratified. So you have denser air at the surface and lighter air above. These are the two extremes. And then you have something in between, which is the neutral atmosphere. Neither vigorous, neither laminar, somewhere in between. It basically means that there's no tendency to either enhance vertical motion or suppress vertical motion. It's just neutral in between. And as you can imagine, the neutral atmosphere is easier to simulate. You need less stuff. You need to know less about the stratification. And the stable and unstable, in particular, the stable one is more difficult. But nonetheless, for the same wind speed at hub height, how come it's so different? And here are some examples for a single turbine. The first row is stable, neutral, and unstable at the bottom. And the first column is right behind the rotor, right after the atmosphere has interacted with the turbine. And all these reds indicate that there's a deficit, right? There's a wind speed deficit. The darker the red, the more the deficit. And as you can see, but the hub height, the geostrophic wind, the wind aloft is the same for these three cases. So in terms of large scale condition and weather, it's the same. But because of that boiling pasta at the bottom or lack thereof, the deficit is very different. And as you move downstream, now this is 1D, then you go 5D, 9D, you can look at these three circulations. There are streamlines, there's stuff going on that you don't even need to understand all the details. But visually, everything looks different, despite the large scale conditions being the same. So now you put all of this in a farm with 48 turbines, and how much of a difference do I get? And you do get quite some differences. So for the neutral case, you get maybe from the farm 33 megawatts. When it's unstable, you get 35. Again, same forcing. And for the stable case, here you get 30 megawatts. So you get a difference by 5 megawatts out of 30. So it's not a small difference between them. And of course, you can look at more wind directions, staggered versus non-staggered. And it turns out that there isn't a clear rule of thumb. I cannot tell you, oh, when it's stable, it produces more. When it's unstable, it produces less. Because in some cases, you produce more for stable conditions, but in some other cases, you produce less. It all has to do with the alignment of your turbine. So the layout together with the stability, they have to be right to get the best. So it's not like I did a poor job with the simulations. Actually, the observations are very messy as well. I can find papers. These are 3 different papers, 2 of which say that the stable atmosphere produces more, and another one that says, no, you get more power when it's unstable. So there's a mess out there in the observations also. I think I may have some time to talk about compressibility effects also, which is another interesting topic. And here's first the descriptive idea, and then I have a couple of equations. Again, you can check your phone again in a few minutes. The traditional approach to large eddy simulations of wind turbines or flow around wind turbines is incompressible, meaning that the density of air is treated as if it was water. Basically, you can't compress water. And Boussinesq. Boussinesq is this researcher that came up with this very brilliant approximation to make everything easier in solving the equations of the Navier-Stokes equations. So incompressible Boussinesq, IB, is basically what everybody is doing today, including myself. When all the results I showed you earlier, incompressible Boussinesq. And now we're working on a non-incompressible, non-Boussinesq. So NIMB, non-incompressible, non-Boussinesq. It's not truly a compressible simulation, so that's why you can say, why do you say non-incompressible? Just call it compressible, but it's not exactly compressible. So the differences between the two is that the main difference is that density varies actually in space and in time in the non-incompressible, non-Boussinesq, whereas in the incompressible Boussinesq it wasn't. It's assumed to be constant. And also, the wind is not solenoidal. So the divergence of the wind is not 0 in the NIMB approach. And so the underlying assumption of this is that the fluctuation of density, of air density, are not that important, or they don't matter at the scale of the resolved features. So basically, let me transform it into equations. Density, which is rho, is assumed to be constant, equal to rho 0, or sometimes is a function of z only of the vertical. But here, density is equal to its resolved scale version counterpart, and it's a function of x, y, z, and t. So it's a fully 3-dimensional and time-dependent variable. So once you do this change, you basically see rho bar more often in your equations, but there aren't actually a lot of complicated terms. And so you can use this new framework now to study the wakes. And here are some results of the single turbine. The top one is compressible, or NIMB, and incompressible. And at first sight, they look very similar, which is what I expected. So even though the blades spin kind of fast nowadays, you can get maybe to about 100 meters per second at the tips in terms of the speed of the blades. So the Mach number is, a third, something like that. So that was the motivation why I thought this could be interesting. But for the speeds that I'm showing you here, which are 10 meters per second, there shouldn't be dramatic differences, but some nonetheless. So here is the difference between the two. And you can see 2 main things. One, that upstream of the turbine, there's some blue. And blue means that there's the speed difference between the two is negative. So when I use the compressible assumption, the speed in front of the turbine is less. And if the speed in front of the turbine is less, the power will be less, because they go hand in hand. So if the power is less, it means that what I'm left behind is a little bit more speed. And in fact, the second feature is the red behind the turbine. So there's more speed left downstream of the turbine when you use this compressibility, when you don't neglect compressibility. And we're talking, again, about 0.2 meters per second, 0.3 meters per second difference, so not a lot. TKE, though, is a little more sensitive, and an important parameter that matters is actually the tip speed ratio, which is the TSR, which is basically the ratio of how fast the blades are rotating over how fast the wind is. And that's where the TKE difference, here are 4 cases that we looked at with different combinations of them, but the tip speed ratio tends to gets bigger as we go down this column, and the TKE, again, becomes different. So there is less TKE when we consider the compressibility effects. So we're looking at what happens when you have multiple turbines, when the wakes overlap. But again, I'm not talking about differences on the order of 10%. That's what we get when we get a smart layout. I'm more talking about maybe 1% differences. But again, why make a 1% error if I don't have to? That's the motivation behind this. So in conclusion, I would like you to remember what wakes are, and I hope that those photos will give you an impression mentally. But in terms of practically, they reduce wind speed, increase turbulence downwind, and therefore they cause losses. We call them array losses or wake losses, and the bottom line is that they reduce the power in a farm, so we want to avoid them. When you look at the global scale, these wakes are important because if you don't include them, you don't get the right potential. You don't get the right behavior of the atmosphere. And the right behavior is that the Earth system reaches a saturation. You can't extract energy continuously from the atmosphere. At one point, the Earth says, that's enough. You've reached the saturation point. At the regional scale, when you consider these wakes, you can actually interact with large-scale features such as hurricanes or mesoscale features such as nor'easters and have a feedback. In our case, it's a positive feedback, not meaning that it grows. Positive because it has benefits for humanity, for the coastal community. In terms of local scale, if we understand better these wake losses, of course, combined with the stability, atmospheric stability, and combined with optimization, we have a potential of saving money, and if you save money, you make money, right? So you can make money with wake losses, I suppose, and you can save lives if you study hurricanes and protect coastal communities. So that's very cool. And lastly, compressibility effects may not be that negligible after all, and it might be worth it to include them in your simulations. That's all I have. Thank you very much.
Thank you, Cristina. This was extremely nice on let's open the floor for questions.
Most hurricanes have winds around 100 miles an hour or higher. And don't wind turbines disconnect around 50 miles an hour?
Yes, yes. And we did that in the simulations. So once you reach the what is called cutoff wind speed, they shut down. So I was discussing this at lunch. So when we shut them down in the simulation, they don't actually have any drag at all. So even when they're blocked, they still have a little bit of drag, but we didn't include that. So there's a dynamic parameterization that only is triggered when the speed is acceptable. But the nice thing is that the speeds that we have in mind for hurricanes, they tend to be the highest speeds in the hurricane itself, which are around the eye wall, right? The rest of the hurricane doesn't necessarily reach those speeds. And the farm is operating days before the hurricane actually makes landfall. So the story behind this is that the turbines generate all that power maybe 3 days, 4 days before the storm comes, and the speeds are reasonable within the operation range. But all that energy that is taken away from the storm starts trickling into the main feature of the hurricane before it even comes. So when it actually comes, they are shut down. But they have already done the damage. Over here.
So it's interesting to look at the feedback on the hurricanes in the Gulf of Mexico.
There's other features of the Gulf of Mexico where I wonder if the effects of wind turbines might not be deleterious. One of the big issues is for both fish production and also human health is anoxia and hypoxia. And a lot of that is due to increased nutrient loading, but when you have strong wind mixing, that tends to help bring oxygen down. And I suspect that at these lower wind speeds, not hurricanes, this might be a larger effect. Have you considered that?
No, I have not, but that's actually, so I think what you're saying is that it might be actually detrimental to the problem. It could be. At the same time, though, there will be strange patterns of divergence and convergence that may or may not help, because you have a localized area with lower speeds, but outside it's the same. So maybe there's some strange mixing that could not be necessarily detrimental. And anyway, as I said, when the actual wind comes, they are not doing anything. The turbines are stopped. But that we can, if you have a model that can look at that.
So Cristina, how much of this effect on the hurricane is kind of extracting mean kinetic energy and kind of slightly slowing it down versus maybe messing with its source of energy, which is the ocean, or maybe is this wind turbine kind of slightly reducing the amount of latent energy and other thing it can pick from the ocean, or is it reducing the source, or is it just a slow drag on it?
It definitely is a drag, that is for sure, and I suspect that is the dominant parameter, also because of the divergence and convergence patterns that we have seen. So we know that slowdown is not small. It actually creates these convergences. But that's an interesting question. And the model that we're using right now, WRF, as you probably know, is pretty complicated. It's complex, and it has exchanges at the surface. And we did not touch those. So all we did was add this term in the momentum equation, which eventually makes its way into everything else. I have not looked at maybe the heat fluxes or the latent heat fluxes, if they are affected. Most likely they are. I don't have an answer. But I would guess that the direct effect of the slowdown and the enhanced drag is probably an order of magnitude higher. But I will look.
Talking about stability, you showed that actually there's quite a bit of a wind deficit depending on the stability. Now what might happen is that actually turbines in like the second or third row may, because of the deficit, feel a different regime of stability, a changed stability, because you simply change your mean wind speed that is determining the stability. So do you have any ideas how that might affect your like zero-dimensional models or their performance, or what that might do to the farm layout or implications thereof?
This is such a good question. And that's why I said that the more I study stability, the less I understand it, because the explanation I gave earlier with the past, etc., is basically just static stability. It doesn't really take into account the wind. It's just thermal stratification or not. But stability is more complex than that. The effect of wind, the distribution of wind in the vertical affects it, and the momentum exchanges and whatnot. So you are absolutely right. As soon as you start affecting the vertical profile of speed, you affect the stability itself in its more advanced term. Having said this, in the simulation, I haven't shown you many details of the unstable and the stable runs, but those we have basically created fit-in parameters for the zero-order model that are for unstable conditions, stable conditions, and so we have 3 sets of parameters for those conditions. And even though at the local turbine, I cannot tell you exactly how it's changed, what I know is that the LES does it properly. And so by fitting the proper LES to the proper case, I get these fitting coefficients that miraculously take that into account in a linear fitting kind of way. But you're absolutely right. I mean, once you start altering the vertical distribution, the stability is affected for sure. But the good news is that LES has that as the simulation evolves. So 4 questions on hurricanes, 1 on something else.
So in fact,
I should have expanded that part of the talk.
no, I mean it was fantastic. The big picture and the small details. I think everybody got what they came looking for. So
Good,
thanks again.
good.
We'll thank Cristina once again.